morning, everyone. Today, our topic is the application of linear systems in complex electrical networks using Kirchhoff's laws. Our presentation focuses on one main question: how can a complicated electrical circuit be converted into a matrix equation solved by linear algebra and then used to make engineering decisions? In real-world electrical circuits, engineers often need to find unknown node voltages and branch currents. These values are important because they tell us whether the circuit works safely and correctly. For a small circuit, Ohm's law may be enough, but for a circuit with many nodes and branches, solving each part separately becomes inefficient. Linear algebra provides a systematic method. It allows us to write all circuits' relationships together as system of linear equations. The standard linear algebra form is Ax equal to b. In circuit analysis, the vector x contains unknown voltages or currents. The matrix A contains coefficients from resistance or conductance values. The vector b contains independent sources, such as current sources or voltage sources. So, in this topic, Ax equal to b is not only an abstract equation, it's a mathematical model of an electrical network.
Build a linear system with Kirchhoff's law. First, Kirchhoff's current law, or KCL, says that the total current entering a node equals the total current leaving the node. This is based on a conservation of charge. Second, Kirchhoff's voltage law, or KVL, says that the total voltage raise and the voltage drop around the closed loop is zero. This is based on the conservation of energy. In our example, we might use KCL and nodal analysis. If two nodes has voltage Vi and Vg, and a resistor R connects them, the current is I equals Vi minus Vg divided by R. This expression is linear, so KCL naturally gives a linear equation. The process has 5 steps. First, choose the anodes. Second, apply KCL at each anode node. Third, use Ohm's law to express branch currents. Fourth, arrange the equation into matrix form. Finally, solve the matrix equation and interpret the result as an engineering decision. This connects the circle problem to linear algebra directly.
Now we use a 3-node circuit as an example. The unknown voltages are V1, V2, and V3, measured with respect to ground. The circuit has 5 resistors. R1 equals 6,000 ohms from node 1 to ground. R12 equals 3,000 ohms between node 1 and node 2. R2 equals 4,000 ohms from node 2 to ground. R23 equals 2,000 ohms between node 2 and node 3. R3 equals 12,000 ohms from node 3 to ground. There is a 5 mA current source into node 1 and a 2 mA current source into node 3. Our task is to solve V1, V2, and V3. At node 1, the 5 mA current leads through the 6,000 ohm resistor and the 3,000 ohm resistor. V1 over 6 plus V1 minus V2 over 3 equals 5. At node 2, the currents through all connected branches must balance. V2 minus V1 over 3 plus V2 over 4 plus V2 minus V3 over 2 equals 0. At node 3, the 2 mA current leads through the 12,000 ohm resistor and the 2,000 ohm resistor. V3 over 12 plus V3 minus V2 over 2 equals 2. After simplifying these 3 equations, we can obtain the following linear system. Now the circuit has become 3 linear equations with 3 unknowns.
Now we focus on the mathematical structure of the matrix. In nodal analysis, the coefficient matrix is called the conductance matrix. Conductance is a reciprocal of resistance, G equal to 1 over R. The entries of the matrix follow fixed rules. For the diagonal entry AII, we add all conductance connected to node I. AII equal to sum of G connected to the node I. For an off-diagonal entry AIJ, if node I and node J are connected by a resistor, then Aij equal to negative Gij. If node I and node J are not directly connected, then Aij equal to 0. This explains why the matrix has positive diagonal entries, negative off diagonal entries, and zero entries. The matrix pattern directly represents the circuit topology.
Using the three KCL equations, the matrix form is as shown on the screen. This is exactly AX equals B. To make calculation easier, we multiply each equation by 12. This gives an equivalent system as shown on the screen. This step does not change the solution. It only removes fractions and makes the system easier to solve.
Before solving, we can use linear algebra to check whether the solution is unique. For square system AX equal to B, the solution is unique if A is invertible. A matrix is invertible if its determinant is not zero. For a fractional matrix, determinant A equal to 1, 0 lie over 864, since 109 over 864 is not zero. The matrix is invertible. For the integer scaled matrix, the determinant is 218, which is also non-zero. Therefore, the circuit has exactly one voltage distribution. In engineering terms, the mathematical model gives one definite physical answer. Next, we solve the system using Gaussian elimination. We start with the augmented matrix. Gaussian elimination uses elementary row operations. These include swapping rows, multiplying a row by a non-zero constant, and adding a multiple of one row to another row. These operations do not change the solution. They only transform the system's simpler equivalent form. After row reduction, the reduced row echelon form is. Therefore, V1 equal to 1938 over 10 lie, V2 equal to 1272 over 10 lie, V3 equal to 1464 over 10 lie. This shows how row reduction directly gives the circuit solution.
Converting the exact fractions to decimals gives V1 equals 17.78 volt, V2 equals 11.67 volt, V3 equals 13.43 volt. Now we calculate branch currents. The current through the resistor between node 1 and node 2 is I12 equals V1 minus V2 over 3000 ohms, which gives us I12 equals 2.04 milliamperes. The current from node 2 to ground is I2 equals V2 over 4000 ohms equals 2.92 milliamperes. The current from node 3 to node 2 is I32 equals V3 minus V2 over 2000 ohms equals 0.88 milliamperes. These results turn the mathematical solution back into electrical quantities. We can also verify the result using the KCL. At node 1, the input current is 5 milliamperes. The current through the 6000 ohm resistor is V1 over 6000 ohms equals 2.96 milliamperes. The current from node 1 to node 2 is I12 equals 2.04 milliamperes. Adding them gives 2.96 plus 2.04 equals 5 milliamperes. So the total outgoing current equals the incoming current. This confirms that our linear algebra solution is consistent with the physical law of conservation of charge.
Now we connect the mathematics back to engineering. The linear system gives no voltage and branch current. Engineering uses the value to make a decision. If a calculated voltage is higher than the safe rating of component, the engineer may choose the component with higher voltage rating or radius than the circle. If a branch current is too large, it may cause overheating or component failure. Then the engineer may increase resistance, change the circle structure or its potential component. Therefore, the matrix solution is not just a numerical answer. It helps the engineer predict circle behavior before building the physical circle. This reduces trial and error testing. improve safety, and make circuit design more efficiently.
This method is used in many engineering applications. In electronic engineering, nodal analysis is used in amplifier circuits, filter circuits, sensor circuits, and printed circuit boards. In power systems, matrix methods are used to estimate voltages and currents in distribution networks. In circuit simulation software, the program converts circuits into equations, builds metrics, and solves them automatically. The same idea can also be extended to AC circuits using impedance. In case, the unknowns may become complex numbers, but the structure is still a linear system. For nonlinear components such as diodes or transistors, engineering often linearize the circuit around an operating point and solving the sequence of linear systems. To conclude, Kirchhoff's law and Ohm's law convert a circuit into linear equations. Matrix representation, determinant, and Gaussian elimination solve the equations. The final voltages and currents help the engineering judge safety, prevent failure, and improve design. The main message is linear algebra turns a complicated electrical network into a structured and solvable system. It allows engineers to understand, predict, and design circuits in a professional way. Thank you for watching.